Kusazangpola, welcome back to our deep dive. Today, we're getting into something pretty fundamental, electrical resistance.
Right. It's all around us, but what actually makes it harder or easier for electricity to flow?
Exactly. You shared some really interesting material, and, well, our mission is to unpack that, figure out why some stuff lets electricity flow freely and other stuff just, resists.
Sounds good. So resistance, at its heart, it's just opposition to the current. Think electrons trying to move through a material.
Like people trying to push through a really crowded hallway.
That's a great analogy, actually.
Yeah.
And the first thing that determines how crowded that hallway is the hallway itself, the nature of the material.
Okay, yeah. Copper, aluminum, they always come up as good conductors.
They do. And it's down to their atoms. Copper, for example, it has electrons in its outer shell that aren't held very tightly. They're easily freed up to move.
Ah, so lots of free electrons means it's easy for the current to flow, like an open door.
Exactly. Loads of available charge carriers, that gives them really low resistance.
But then materials like, say, iron or nickel, they're more like that crowded hallway scenario.
Precisely. Fewer free electrons, more intrinsic opposition to that flow. It's built into the material structure.
Got it. Okay, so material type is number one. What about the length of the wire?
Good point. Imagine making that hallway longer.
More chances to bump into people, slow you down.
Exactly that.
Hmm.
The longer the path, the more collision those electrons are going to experience. The sources clearly show resistance is proportional to length. RL, as they say.
Simple enough.
Yeah.
Longer path, more resistance. Now, what if we make the hallway wider?
Thickness, or technically the cross-sectional area.
Right. A thicker wire feels like it should be easier, like adding more lanes to a highway.
And it is. A larger cross-sectional area, A, gives the electrons more room to maneuver. Fewer collisions, less congestion.
So resistance goes down as the area goes up?
That's it. It's an inverse relationship. R is proportional to 1 over A. More space, less resistance.
Material, length, thickness.
Okay, but what about temperature? Heat usually makes things trickier in electronics, doesn't it?
It certainly does, usually. For most conductors, like our copper wire, when it gets hotter, the atoms themselves vibrate more.
Creating more obstacles, like the people in the hallways suddenly start jumping around.
Kinda, yeah. More vibrations mean more interference, more collisions for those poor electrons trying to get through, so resistance goes up with temperature.
Okay, standard behavior.
Yeah.
But then there's the exception you flagged, semiconductors,
Yes.
like silicon.
Yes. This is where it gets really interesting. For semiconductors, increasing the temperature can actually decrease resistance.
Wait, the opposite. How does that work?
Well, in semiconductors, heat can energize electrons, freeing them up to become charge carriers. So while the vibrations do increase, you also get significantly more electrons available to carry the current.
So you're adding more messengers, which outweighs the effect of the slightly more chaotic path. Exactly. It's a different mechanism dominating. So for semiconductors, higher temperature often means lower resistance. It's quite distinct.
Fascinating. So let's pull that together. We've got the material itself, its atomic structure. We've got the physical dimensions, length and thickness. And then temperature, which, well, usually increases resistance, but does the opposite in semiconductors.
That covers the key factors, yes.
Hmm.
Understanding those gives you real insight into why things are designed the way they are.
Right. It's not arbitrary. It dictates everything from power line design
Definitely. Managing resistance over long distances is crucial there.
to the tiny circuits inside our phones, where managing heat and resistance is, well, critical.
Absolutely critical.
Yeah.
Efficiency, heat dissipation, it all comes back to these principles.
So hopefully, for everyone listening, that gives you a clearer picture. It's not magic. It's this interplay of physics and material science happening whenever you use electricity.
It really is a neat dance between matter and energy.
Which leaves us with a thought, perhaps. Engineers are always working with these factors, but how might totally new materials change the game in the future? Could we get even better conductivity, even more efficiency?
That's the cutting edge, isn't it? Finding materials that push these boundaries.
Something to think about. Tashi Delit Kadrinje.